like to welcome Fernando Perez to our distinguished lecture series.
Thank you.
He's going to, of course, he's going to talk about Jupyter notebooks. And the big deal here is he's trying to put the science into computer science so that we actually have reproducible experiments and that you can make your data available to people and the algorithms and your analysis techniques. And the other part you do is you put it all into web pages, and so you make it cool. So Fernandos is cool. So maybe someday I will be, but right now Fernandos is. So I'm looking forward to this talk.
Thank you. Well, first of all, thanks for having me. Thank you all for having me, folks. It's my first time in Vancouver. I've really enjoyed my visit so far. I have some existing connections to folks here, but it's been absolutely great to be here, and it's already been very, very productive. Very quickly, a couple of bits about sort of where I come from. My background, I'm originally from Colombia, and this actually will be relevant in a moment. It's not just bio. My background is in physics, so I did work as an undergraduate in physics, in dynamical systems, chaos and the electrostatic free-body problem. Then I did a PhD at CU Boulder up in the mountains in particle physics. It turns out that Ian and I both worked exactly in the same dark corner of high-energy physics called lattice QCD. A career path that led me to this. So I have that to say for that in public, and that's about it. But I spent a lot of time building numerical tools and computational tools for data analysis. And while I was doing my PhD for analyzing this data in lattice QCD, some of the ideas that we'll be talking about kind of were born in that context. But a lot of these ideas, for me personally, do have a Canadian connection that dates back to when I was an undergrad. So this is a plot of both the trajectories of the electrostatic three-body problem, where you take three particles with obviously two with one charge and one with the other, and you try to compute its dynamics. That's what I did as my undergrad. And I don't have screenshots of my original Maple notebooks, but that was my first introduction to these systems, was using Maple to do the derivation of the analytical transformations that were needed for the system to be numerically solvable, and then to do code generation out of the analysis to then plug that into the numerical codes that led to these are the Poincare sections for the various orbits. So in my personal case, this story sort of intellectually does connect back to Canada thanks to Maple. With that bit of context, I'd like to motivate for a second sort of why this all happened. Sort of what are the kind of ideas that drive me personally to this, and there's kind of a couple of different things. To me, they're all important. One is kind of this, what I would call an ethical consideration about openness as an enabler of fairness. That's why I mentioned where I come from. When I came to Boulder, I did have access to, it turns out that when I got to Boulder, I switched from Maple to Mathematica, just because that's what they had in the department. They had licenses for Mathematica. I had access to IDL. I had access to all of the proprietary tools that I wanted. Those same tools were not as easily accessible to the people who did, to my mentors and my colleagues and my professors back in Colombia. The cost of the license of those packages in Colombia relative to the economy was a huge barrier to entry. And so I would like to do my work with tools that would allow me to access that work and share it with others, regardless of economic barriers to access. It turned out that this was something I discovered. I wasn't expecting it, but it was a huge driver for me personally, became the human and social element. This idea that by building tools in the open, you find other people like you out there. Those people do exist, and the internet helps you find them, and you can actually build a community of like-minded people who are interested in making these things. And everything I'm going to show was built out of weird collaborations that happened across traditional disciplinary boundaries. People who on a campus would never have a reason to talk to each other, but who found each other by virtue of wanting to build these tools together. And for me, that was a huge driver. There's what I would call an epistemological motivation, the notion that I do not consider acceptable the idea that scientific work whose mission is fundamentally to understand sort of nature, how is the world put together, and that the tools we use for that understanding have a layer that says if you can open nature, but if you open me, I will sue you. Right? To me, that is anathema to the very essence of what science is. So proprietary tools in the path of scientific discovery, I think, are just fundamentally kind of epistemologically broken. And then finally, just Python was cool. I just fell in love with the language. I'm a geeky physicist. I like to code, and I fell in love with Python. I had piles of Perl to babysit all of my simulations and all of my analysis. And then when I discovered Python, in 24 hours of having done the tutorial, I knew how to do things in Python that I had no idea how to do in Perl. And that's when I realized this tool is cool. I'm never writing a line of Perl again in my life, and that was true. I said that in October 2001, and I haven't touched Perl in almost 20 years. What is it? What did we do? And so the big picture of the what is that we have a limitation, which is the size of this thing, and it doesn't get better with age. This is not internet scale. This is not disruptive, right? There's no paradigm change in here. None of the Silicon Valley lingo applies to this bag of meat. It is what it is limited, and whether the computations we do are being done on a small kind of laptop-sized machine or a huge computational resource, that's Cori, the new supercomputer at LBNL, whose front end now, very popular, is a Jupyter interface. Jupyter and IPython, this machinery is kind of the layer for computing where humans are driving the question. So that's really where I exist. Even though my PhD was in sort of supercomputing and analysis of particle physics data, my postdoc was in the development of algorithms for PDEs, where performance and numerical correctness were kind of the drivers. What I've ended up really building along the way is tools for the bridge between humans and the computation, and for dialogues between humans and computers. So for humans to use the computer as a thinking environment, and for humans to communicate with each other, those computational processes. So the human in the loop as the thinking machine, regardless of the scale of the problem, is sort of our driver. And the fact that we're trying to bridge kind of the gap from small lightweight interaction to very large scale computation poses some interesting challenges. This machinery began kind of as a teeny bit of Python. I've actually posted a while back on GitHub what was IPython 001, like my first afternoon hack when I told my advisor I'd be back the next morning. It's been 18 years, so never believe me what I say about time estimates. But it began its life as 259 lines of little Python. It still has my email address. You will recognize Pi0. That was the name of the high-energy server in Colorado. People that you know in the Lattice community probably had those emails that you still have in your inbox. Over time, it evolved into an interactive system that really was basically capturing the kind of workflow. We didn't invent this. It's the kind of workflow that is very natural in many computational systems. The standard Unix shell has the same thing, kind of the venerable REPL, the read eval print loop. It reads your input, it evaluates it, it prints it, and it waits for you, but with an important kind of twist over something like the shell, which is that in scientific environments, it's useful for these things to combine a programming language with things like object introspection, file access to plots, operating system management, to be able to run a script and inspect the state of the computation midway, because what you do at every step of the way is typically driven by what you've just done, right? These are not really tools for software engineering as much as they're tools for using the computer for exploration of data and computational problems. So even though all of that began its life as a personal sort of, I'm going to hack on this thing for an afternoon because it's fun. It's more fun than working on a dissertation. Today, I really have to get, like, the credit for everything that I'm talking about does not go to me. It goes to a huge team of people who are building this day in, day out. These are two pictures of two of our biannual meetings of the people who spend kind of close to full time of their working life in things connected to Jupyter and IPython. This is a range of people who go from academia to industry. There are people there who work at, Jess is now at Google DeepMind. There are people from Bloomberg. There are people from Anaconda, Continuum Analytics. There are people from a variety of companies, people from Wikimedia, and from academic institutions. And we've kind of managed to cobble together this weird collaboration between academia, industry, government research. This is at LBNL, and a very large community of contributors. Some of you here in this room have contributed to these tools, and I hope many more will. So very quickly, who here has not used the IPython notebook, Jupyter notebook in the room? So so for those of you who haven't used the tools, and I asked it that way because I know many of you have, and it's easier to count the nods right now. So for those of you who haven't, this is the evolution of the same idea that we have in a terminal where you type some code and you get the answers, but ported to a document-based environment. And so what we built was eventually, and I'm skipping over years of development and many missteps, what we built is a system where you can type natural language, you can type text. That text can include mathematics and it's rendered live. You can also type code, and at the beginning it was code in the Python programming language, and you will have the output of that code execution be stored right there next to you so that you can combine natural language and computational languages. You can store the output. All of it is contained in a document, so this is actually a file that can be stored as a document. And furthermore, as you see, the window where this is running, the graphical interface is actually a web address. So it's actually a web server that is running this, and the client is actually a web client. And this will be important because what happened was we sort of embraced the idea of the web. The Maple notebook that I was showing at the beginning, that was a graphical interface written in, I don't know what, probably C++ and some Windows toolkit. Our early attempts at building this were actually also graphical interfaces written, in our case, in WXPython. We had a tool written in Qt that did a few of these things. It's very, very hard to develop good graphical interfaces. That's the kind of stuff that requires really large teams of engineers. We were able to piggyback on the battle between Google, Apple, Microsoft, and Mozilla, who were pouring obscene amounts of engineering resources into building high-performance JavaScript engines, high-quality graphical interface tools on the web, and that the world was standardizing around this. And this gave us the machinery that allowed us to build the kind of interface that we needed with a very, very small team and kind of riding that wave of engineering work. But it also proved to be a very useful decision to make because by building a tool that was web native and web first, the difference between local execution on a laptop and remote execution on a supercomputer or a cloud environment basically goes away because the entire architecture has been designed in the same way across those things, and that really has made a huge difference. I want to try to highlight sort of what are the core ideas that underpin this system by way of an analogy with something which is very familiar to all of us, which is, in a highly simplified manner, you can kind of think of the web as built around a protocol, HTTP, the Hypertext Transport Protocol, or its secure flavor with an S at the end. This is the protocol that was built to connect clients and servers that transmit data encoded on the protocol. And by and large, when we connect to HTTP servers, we're connecting with web browsers, right? Our human interaction with HTTP is typically an interaction mediated by a web browser, but it doesn't have to be. You can build web services that use the transport of HTTP to build services that are accessed by other machines. You can build REST services. You can access them over the command line. There's many ways in which the protocol is not necessarily attached to the rendering of a web page. Now, when the data that travels over that protocol is designed to be rendered to a human, when it's meant to become a document, we use HTML. And HTML is a way of encoding that traffic and storing and representing it, and then browsers do the job of rendering that and turning it into content that you can read. So we have something kind of similar. There's a protocol that effectively tries to abstract the things we found we were doing. We literally went through, like, what is it that you do when you're working interactively? When you're doing human-driven computation, what do we do? And we made a list of those things. And then we said, okay, we are going to encode these things into a properly formalized protocol. We're going to define a protocol for clients and servers to execute these actions. The things that were implicitly in all of the APIs of the original IPython, which had no concept of clients and servers. It was a Python process that would just read standard in and do things and produce standard out, but it did a lot of things. We basically went through the whole thing and wrote down what it did and turned that into a generic protocol. That protocol specifies the transport of information encoded as JSON and a set of very specific connection patterns for the network traffic using a library called 0MQ. This was a really fortuitous choice that we found. It's a library written in C++, very, very minimalistic C++, no dependencies, very clean, very tight code, very high performance, and with bindings in just about any language you can think of. So, by virtue of defining this communication pattern of what it means to do interactive computing and representing it on top of a connection pattern deployed by a library that is easily accessible to any programming language, and the traffic itself being encoded in JSON, which is these days just about any language has a JSON encoder and decoder available to it, it means that you can implement this protocol in virtually any programming language, and this will be important in a minute. When that traffic, when that pattern of communication wants to represent something which is itself a document, we also encoded that into a format. And so we actually defined a format, and we defined tools to take that format, which is data-driven, it's actually a JSON data structure internally, and represent it whether as an HTML page, or as a PDF, or as any other form of output that you might need. Now, that protocol, as I said, tries to capture what is the process of doing computation interactively. It can represent basically, it's kind of the REPL for the web. It's the idea of what is the output of a standard computational process. If you think of the traditional Unix model, any process that you create on a system, you have access to standard in, standard out, and standard error. Standard out and standard error are two channels that produce text, and that's basically it. What we did was we just sort of did that, but with a MIME type in front, so that you can produce the same outputs, but anything that you can tag with a proper MIME type, which means that a browser will consume and will know what to do that with, you can produce. So if you produce textual output, we'll represent it. If you produce an image, we know what to do with it, and we'll represent images. If you produce LaTeX or PDF, we know how to represent it properly as mathematical output. If you produce HTML, obviously that can be rendered in a browser. And you can even produce traffic that includes live interactive controls. And we actually have established a communication process for client-side interactive controls to drive the back-end computation, so that as you move, say, a slider, the actual computational back-end is running with only writing one line of code. Like, so literally in here, when you write factor, this is using SymPy, the Python symbolic library. This function is designed to factor the polynomial x to the n minus 1. But by virtue of adding that little one line that says interact, you automatically get a control that calls the function as you drive it. So it makes it easy for a scientist who isn't going to be writing GUI codes extensively to add live exploratory controls to your code. And this is now being very widely used both in education and also as a research tool, as a way of basically building, I call them just-in-time GUIs. Basically, you have a few little controls to do live exploratory interactive control of parameters in a specific setting without having to build an entire application, which used to be kind of the typical thing in a lab when you decide, okay, we're doing this thing a lot, now we need a GUI for it. Who's going to go write it? And like somebody, well, I'll spend a few months learning how to write a GUI, and I'll be back in 3 months. So the idea is, instead of doing that, you drop a couple of lines of code, and you have basically small live controls kind of on-site and on-demand as you need them. But by virtue of building this protocol in this somewhat generic fashion, it became possible to write code where the backend was not just Python, but, for example, Julia. So we got together with the Julia team. Who here uses Julia, or at least has played with Julia? Okay, so a few of you. Very cool language. We met the designers of Julia early on in this process, and I personally, because of my background, was very interested in the language. I think they're doing phenomenal work. And we got together with them, and we realized, wait a minute, we can actually hook up our backend to Julia pretty easily. And then at one point in 2013, we flew them to Berkeley to one of our all-hands meetings, and we were meeting in one side of the room. The three of them were sitting at a table at the other end, and they were basically trying to implement in Julia our protocol. And as they ran into snags, because it was early in the days of, they would just walk over and ask us, hey, you guys didn't document what happens here. There's an ambiguity here in your docs, and we would just explain it to them. And we started Monday. By Wednesday around noon, they had a Julia kernel up and running, implemented natively in Julia. So it took about 2 days. We did the same thing with Haskell, with R, and after doing a couple of languages, obviously every time we would realize, oh, we kind of leaked a few assumptions about how Python works into the protocol. This isn't generic enough. This language has this funny property where this should be represented in this way instead. But after ironing those kinks, from basically doing n equals 1, n equals 2, n equals 3, and these kind of developments, so we did it with Julia, we did it with Python, we did it with R, eventually we kind of had a model that was generic enough for others to adopt. And at this point, if you go and look at the list, there's about kernels that implement this computational protocol for about 100 programming languages out there, or at least about 100 kernels. Some of them are duplicates. Many of those things are like weekend toy projects that don't really run very well. Others are industry tested, extensively battle-tested tools. But the point I want to make is that this bet basically paid off. This bet of abstracting these ideas, documenting and representing these protocols, and now building the infrastructure that would encode all that, paid off in the sense that now the community has adopted these things widely out there. And if you have an environment where you have teams working on in different programming languages, and Ian, yes, there is a MATLAB kernel. If you have teams working with different tools, as long as there are kernels available for it, you don't have to go reinvent everything. And at the layer of human interaction, at the level of human communication, at the level of deployment, of document conversion, et cetera, that operates in an identical way. Because if you want to take advantage of the rest of our ecosystem, the only thing that you need to produce is the right kernel implementation, and the rest of the machinery is completely agnostic to that. Now, along the way, we had what we call the Jupyter Notebook, which you already saw a screenshot of. When you actually open the notebook, in order to know what file you're going to open, well, we have to give you some tools to access it. So there's actually a file manager. It turns out that if you're working on a remote machine, it's really handy to have access to lower level access to the machine. So there's actually a terminal emulator in there. There's also a regular text editor if you need to edit files. So over time, what we call the notebook was really becoming this kind of application to do many different things, driven by need. This was purely driven by our needs, typically operating on remote environments and servers. And so over the last few years, in a very close partnership with both Bloomberg and Anaconda, formerly known as Continuum Analytics, we've been developing what is called Jupyter Lab. It just went into official public beta. I mean, it's been open source since the beginning, but in kind of usable beta a few weeks ago, or technically, I think it was last week. And Jupyter Lab is sort of the distilling of the lessons of everything we've learned about the workflows and the usage patterns of the Jupyter Notebook machinery and the architecture, trying to condense it into not only an application, but a much more modular architecture that, yes, does the same things, hopefully does many of them better, but is also extensible so that new interaction patterns can be designed, so that new tools can be built that attach to these computational processes that produce these documents, that implement these ideas. So let me try to see how bad this goes by doing a little bit of a demo. So I do have cheat notes for what I'm going to do. Let's see how this goes. So this is what Jupyter Lab looks like. If anyone here has used something like Visual Studio, it's not all that dissimilar. We've taken cues kind of from many other environments that exist out there. We still have the classic notebooks. It still works. So if I open a traditional IPython notebook, I can still run it. This is an example, by the way, to show you how the IPython notebook is capable of running not only of running Python code, but also running in the same block. Oh, by the way, let me crank up the font size still a little bit so the folks in the back can see a little bit better what we're doing. One less. So this is an example of in Python asking for loading the RPy2 IPython support. RPy2 is a process that bridges between R and Python. And then I can say, if I've created X and Y as these two arrays, I want to write a block of R code. So this $R says the following block is actually R code, but I want R code to operate on my X and Y Python variables. I'm going to build a linear model, just as a simple linear regression of Y as a function of X. And I'm going to compute the coefficients of the linear model here as XY coef, and I want to get that back. So when this block of code runs, any of you who's familiar with R is going to recognize this as the standard output of the summary of a linear model in R. But here I have XY coef as a Python variable that I can continue operating with. So I can be working in a Python environment, but basically take advantage of R. This is an example of something called Cython. So for those of you who haven't used it, Cython is this funky little hybrid language where you take Python code and you extend the Python syntax with a little bit of basically C-type declarations and low-level C access. And then the Cython tool takes that source code and generates C code that may have much better performance than Python. And so this is an example of grabbing a little bit of Python source and then basically saying, if I run this under Cython, all I need to do is make a couple of changes to the syntax, and now I get potentially faster code. If I want to know how fast it's going to be, I can ask Cython to give me an annotated output. And what Cython does is it will shade the input source with yellow. And each of these, I thought it was supposed to, these were supposed to expand. Oh, okay. Oh, I think this must be a little Jupyter Lab bug that we haven't fully, we don't have this expansion interaction, because the idea is these lines, the yellower the line, the more the Python code is doing under the hood, so the more expensive it's going to be. Since this is typically done as an optimization step, you want to know where is my Python code requiring more and more computation under the hood so that I know where my hotspots are going to be without having to be an expert in the internal workings of the compiler. You can do the same thing with Fortran. So this is an example of saying I want to be able to write Fortran inline. And so here we have a block of Fortran, and then we can call it live. So this is sine of x cubed minus cosine x. If I change this to sine of x squared, I can use basically Fortran as a scripting language along the way, accessing my Python data. So this is an example just of kind of what the IPython notebook does. It still works the same in Jupyter Lab, so we didn't kind of throw the baby with the bathwater. This continues to exist. One thing if anyone here has developed educational content with this, with Jupyter, you probably have suffered the misery of trying to edit content across notebooks. Who here has tried to move content between notebooks? Okay, you probably hate us because it's horrible. So you'll be happy. You will be happy when I show you, if I open this, that if you want to grab these cells, you can copy them. Yes, because it's miserable. And because what you probably have ended up doing, like, okay, I'm going to make a copy of the file, I'm going to open it in VI, I'm going to hopefully count enough braces so that I don't break the damn JSON, right? I'm going to try to match and highlight and copy it, cross my fingers, save it, and try to reopen it. It probably is broken. I'll try that 5 times until I say, screw it, I'm not doing this, right? So now that problem is solved. So you don't have to suffer that ignominy anymore. As I was saying, the tool supports not just Python, but Julia. So this is a native Julia kernel. So in here we're running native Julia code. This is a notebook that is not connected to Python at all. It's just a notebook implemented directly in Julia. Here is a notebook in R. So this is an example of a notebook that is pure native R, standard ggplot calls. This is the standard iris data set in R. So we have the machinery of Jupyter all available to us. But now we can do other things. So for example, let's say that I have a standard Markdown file. We have a text editor. I can say, give me a preview for that Markdown file. So now I have both the Markdown here and a live preview. And as I edit the preview, it renders. But I can also say, well, I'm writing a document in Markdown or in R Markdown, and I actually want computation attached, not to a notebook, just I want computation attached to my LaTeX file or my Markdown file. So I can say, give me a console for this. So the idea is now the pieces of computation of the protocol are available as individual components so that you can connect in any way you want. So if I have a console here, now a console is not a notebook. It's just a raw computational engine where you can type code just as before. You can type even plotting code. Right? But now this console is connected to this document. So I can, as I'm editing the document, I can hit Shift-Enter here, and the document will execute that block of code in the console. So now I can begin building, say, if you're building a paper, you're writing a paper in LaTeX or something, but you want to make sure that you validate your blocks of code, you now have the combination of the text editor, the renderer, and the computational engines that can be attached to it. And this is the kind of thing that you could have done this before, but the bits and pieces under the hood were rather complicated to connect to one another. We still have the same terminal as before, so that hasn't changed. And this is for anybody working sort of on remote servers, having a proper real terminal where you can do all your work is extremely useful. Some HPC centers are beginning to consider actually getting rid of regular low-level SSH access and effectively turning this into the SSH access, because managing SSH clients is a big support drain on HPC facilities. And so they're actually considering doing away with traditional SSH and saying, if you need terminals, they're there for you. And and this is actually simpler from a support perspective, and they can put better, more modern authentication layers in front of it and making sure that people are managing their SSH keys well, putting 2FA and other kinds of things. But now that we have this architecture, it becomes easy, for example, to say, oh, let's connect to GitHub. So this is a plugin that is not part of the default, but that allows me to go and browse GitHub, for example. So this is an example where now I am actually accessing the GitHub, my GitHub account, and I can look at any GitHub account. So if I look at Jupyter, this is the GitHub account for the organization. This is the GitHub account for IPython. And I can do things like, oh, let's open a notebook. By the way, when you have a lot of stuff going on for teaching, it's very useful to just have one document. So there's a keystroke to kind of just have the one thing that you want to work on. So here, I'm actually running a notebook from GitHub. So I didn't have to clone anything. I didn't have to download anything. I'm actually running a notebook directly from GitHub. Obviously, what's going to happen if I save, it's not going to work, because I don't have directly write privileges up into the repository. But I don't know of an easier way to explore data stored on GitHub at this point and more conveniently than this for quick and dirty exploration. So it's sort of an example of the kinds of things that the architecture begins to let you do. In addition to computation, the other piece of this puzzle, of this picture, has always been, as we were saying, data. So we've tried to really make it, really, let me close a few things so we don't. So we've tried to make it really convenient to access data. So let's say that you have the IRIS data set, right, the standard data set that we just plotted in R. If you actually click on it, we will show it to you in a more civilized manner as a standard. We have a table widget that will read CSV files so that you're looking at the data in an easier way. Images can be loaded directly. So when you're accessing, if you're accessing remote images on a server, that's a kind of a standard data set. This is a type of JSON. Who here works on visualization specifically? If any of you is familiar with Jeff here's work on Vega Lite, so this is a JSON file that is encoded with the Vega Lite grammar for interactive graphics. And so because we have, so if I look at it, this is what the default JSON looks like, but we know how to open it and render the Vega Lite, basically the Vega Lite schema with the default canvas render that Vega offers. And so the idea is, for common data formats that are very close to us, we've built a few renders that are attached to the rest of the system, but we make it possible for anyone to actually build your own renders. So this is an example of some JSON that looks like it has a very regular schema. It turns out that this JSON, or let me open this other example here, this JSON with this schema is actually a very specific type of JSON used to encode geospatial data. It's called GeoJSON. So if I open this file with the actual GeoJSON plugin, it turns out that this is the location of museums in downtown DC. So instead of looking at a horrible dump of JSON, I can actually look. We have an OpenStreetMap overlay, and we read the location of the data points and show them on top. So the idea is to give people the ability to use the computational machinery also to access data without necessarily having to write any code. But because it's the same exact plugin, obviously these tools are available in your own computational workflows. This is an example of a data type that if you look at it raw, these are gene sequences, right? This is FASTA, which is a format for those of you in genomics that will probably be very familiar. This is the Zika genome, and these are multiple samples of the Zika genome assembled, but somebody wrote a FASTA reader so that you can actually load the genome directly into the environment with a standard FASTA reader. So we didn't write that. At this point now I'm showing you things that have been done as third-party tools by the community. And one of the things that, so let me actually just to remind you. This idea of interactive controls oh, there we go. So this is what getting an interactive GUI requires. You simply have a function, and if you say, I want it interactive, we will automatically produce the GUI controls based on the type of the data. So if you have, if instead of this, you have right? As you are interacting with the JavaScript layer, it is calling back into the Python code, executing it, and giving you the output. This is all it takes. This is machinery called the IPython widgets machinery. We provide both the backend in Python and the JavaScript control, so that it can be, and that the JavaScript side is released separately, so that other languages can also implement these kinds of interactive controls for their own tools. And here's one example of using, where am I? Of using this for geospatial data. So Leaflet is a library that basically loads geospatial data, and IPyLeaflet uses these tools to give you mapping data and geospatial data, so that with a few lines of code, for example, in this case, we're loading the European base map centered around Italy, centered around, well, the center is probably Corsica and France. But with a couple of lines of code, now we've changed which layers go into the map. So I ran 2 lines of code, and I've added now a new layer on the map. This adds an overlay layer, where now we're saying, as I move over and I hover over it, I have country control. This overlay layer, the specification of how it behaves, is done here in a tiny bit of Python. So here I'm saying, when I hover, I want to fill it with blue. If I say here red, I have interactive controls over the JavaScript layer that are actually defined without, I don't know JavaScript, and I hope I'm not going to have to ever learn too much of it. I'm not particularly fond of the language, but it is the language that the web speaks. So for scientists who want to focus on their computation, this gives you access to building live interactive controls. One more line of code, and you can now, for example, say, oh, I want to know which layers are active. So you can build basically these interfaces where you gradually build the kinds of controls that are relevant to your scientific problem without having to become either an expert GUI developer nor an expert JavaScript engineer. And this is, you're not probably going to develop the next Photoshop with these tools, but in scientific research and in education, often what we need is just the right amount of interactive exploration for the data at hand and the question at hand. We don't need to be building often. I mean, there are cases where that's relevant, but if you get to that point, you probably can invest in somebody dedicating a huge amount of resources for that. But the day-to-day of research and the day-to-day of education is a lot at this level of being able to either explore a problem or illustrate a concept with a small amount of effort. And that's part of what we're trying to do, but built with this modular machinery where these controls can be calling back if you want to. You can make them call back into a large supercomputer simulation, right? You're not limited to what's happening in JavaScript. You do have access to the entire backend. And one thing that I wanted to finally show very quickly that was done recently, was just announced on the mailing list, was somebody said, oh, that looks really neat, but I'm actually not interested in building notebooks. What I need is basically lightweight forms for little sort of GUI type applications in my environment. And he built this tool, he called it scripted forms, where you write a Markdown, you write a simple Markdown file. This Markdown file is just straight up Markdown in a text editor, and then if you call it, if you call that Markdown file with his tool, it actually opens a Jupyter server. It's not a notebook, it's its own document, and now you have the form. If you edit the form, it automatically reacts, but the form itself is built on top of React, and as you modify it, the form actually does execute, in this case, the code that he defined here. And you can do this, cancel this one. This is a more complicated one where the document has a lot more Markdown, and it has things like, oh, let me put a few variables to be plotted. Let me build a data frame where as I add data to it, it computes some summary statistics. Let me add other types of interactive controls, etc. So the idea is he's basically made it possible with a tiny amount. All you do is you write a teeny bit of Markdown and you drop the pieces of computation that you want in here, and you have a live React-based, very responsive website that is connected to a computational backend in Python. I thought it was a really cool example of how, and he actually posted and said, oh, I did all this with the modules that the Jupyter Lab architecture exposes, even though he's not using the interface itself at all. He's just using the underlying pieces and the building blocks of the TypeScript machinery that has been developed. So anyway, that's it for live demos. If I can find my way back to, good God, okay, where did it go? There we go. All right, so in the last few minutes, we did survive that. I do want to talk about how this is impacting, and we're trying to make these tools help the problem of reproducibility in computational research. This is a quote that I've used many, many times. It's a very old quote from John Buckheight and David Donahoe at Stanford. They were actually paraphrasing John Claerbout. Claerbout is a geophysicist at Stanford who kind of was one of the early pioneers of reproducible research. And Claerbout did not promote these ideas out of the goodness of his heart or out of some kind of big mission for making science better. He just wanted his lab to be more productive. He basically said, I'm sick and tired of every grad student coming into my lab and wasting the first year or two of their career, effectively redoing what the postdoc who just left did and under-documented before they left, and they only get to do no work for the last, if they're lucky, 1 year of their studies. I want them up and running in 2 weeks. I want them to get here, grab something, type make sure that it all runs, read what was there, and then start asking new meaningful questions. David Donahoe in 1995, when they wrote their paper on WaveLab, which is a wavelets toolkit analysis package for MATLAB, they wrote this, and I actually think that I very much subscribe to this notion that today, reading the scientific literature if we're reading at the level of a PDF, is a completely insufficient representation of the ideas in computational research, because maybe, I'm sure you're all much, much smarter and harder working than me, but I cannot replicate almost any research these days by simply reading their methods section because it's incomplete. And I know that papers that I have written, no one has a prayer in hell of replicating those results because the stuff that we put in the paper is completely insufficient. The real work was years of writing code and running scripts and writing analysis libraries. And so we're doing a disservice to science by keeping the scientific research output, which is supposed to communicate science, at the level of the finished PDF. So this is an example of a paper that was published recently by 2 scientists in Norway, and they were doing statistical analysis of wind patterns with about 100 years of European data. And they were kind enough to actually, in addition to publishing this paper, putting out their analysis code up on GitHub. So they actually put up a GitHub repository that contained all of their analysis code. And in fact, it was a very close replica. This is a screenshot of the paper on the Royal Society website and of the PDF taken by just zoomed and screenshot the PDF. And this is a screenshot of the GitHub repo. So you can see that it's exactly, they really did. They wrote the paper so that the computation would be in the notebooks that are published, and you would grab the figures from there, and that's what they published as a finished paper. And last semester I was teaching a course at Berkeley called Stat 159, Reproducible and Collaborative Data Science. And as one of the exercises that I gave to the students was, okay, can you make this work? These authors, they published it in the Open Access Journal. They put all their code on GitHub. They put all their data on GitHub. Everything is there. The paper is from November 2016. It was less than a year old at this point. Can you make it work? And the answer was not quite. Even with the best intentioned author, even with almost everything, the students still had to struggle because, of course, there had been bit rot here and there and little things had gone wrong. Now, the interesting thing is this led to actually both Tom Caswell, who's the core developer, the lead developer of the Matplotlib plotting library, and me making both 2 pull requests against the repository of the authors, because what they were missing were teeny little bits and obscure bits of plotting data that had changed, a little bit of sort of insufficient control of state in the random number generators for the Monte Carlo simulations. But the students kind of did all the work, and then we submitted improvements to the paper, and the author actually very nicely sort of responded and said that this is wonderful, and thank you. And so this kind of shows that we are at the point where the idea that Donahoe kind of promotes can be used, and it can lead to a positive feedback cycle. There's nothing lost in doing this. There's actually something to be gained. I don't know this person. I'd never interacted with this fellow. I was looking for a good project for my students, and I just started like, let me look at what's available on GitHub. Oh, this looks nice. This guy seems to have done everything. Let's see what happens to them. And we kind of hit the sweet spot of, yes, it was mostly working, and yet the reality of change in software and dependencies and bit rot and subtle version differences was enough to show the students what life in the real world looks like. The only problem is I can't use it again for the course because we fixed problems, and now it's like completely bulletproof, reproducible, containerized in Docker, etc. So I need to find a new one. But in this discussion, we've come to this tool that was originally created by Jeremy Freeman and Andrew Osherov. Andrew was an engineer in Jeremy's lab. Jeremy is a neuroscientist. He's now at the Chan Zuckerberg Initiative. And this came out of a conversation that Jeremy and I had a few years ago about talking how all these pieces basically were ready to provide the vision that Donahoe was kind of espousing over 20 years ago, of really packaging the research in one single atomic unit, and Jeremy called it a binder, and I think it's a brilliant name. It's not the glossy paper, it's the binder that has all the details, right? And the binder is, you have a GitHub repo, and you describe in a machine-readable fashion the dependencies that repo has. If the repo has the code and data that you need, and in addition you say, these are the dependencies, we can bind all that together into a Docker container that can then be deployed at an arbitrary location, and that will truly be the complete environment that Donahoe was referring to. So they built that. And then something really fun happened in physics that led a couple months ago to the 2017 Nobel Prize in Physics being awarded to the discovery of gravitational waves. If we wind the clock back about 100 years, Einstein had predicted this as a snapshot. That's actually one of the field equations for general relativity, and the field equations for GR predict that the motion of masses in space-time distorts space-time itself, and that distortion travels as a wave, and it travels as a wave at the speed of light. Now, if I flail my arms around here, I am producing gravitational waves. Really small ones, right? Because I am of a small mass. If something of the size of a black hole smashes into another black hole, that's a different story. It's a bigger thing. Detecting even something like that is hard. So this is a device that was built over the last 30 years called LIGO. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And it's really a phenomenal feat of engineering. LIGO is composed of 2 interferometers. For those of you who are not kind of geeks on this topic, let me give you the quick rundown. One of them is very close to you. It's in Eastern Washington at Hanford. And the other one is down in Louisiana. They're separated by about 3,000 kilometers. And what they're made of is 2 arms about 4 kilometers each at 90-degree angles. And these arms have, in the middle, at the junction point, there's a laser and a beam splitter that sends half of the beam in each direction. Light bounces at the end at a mirror and comes back. Right? And so because it's coherent light like this one, as long as everything stays the same, the waves go in and out in phase. And there's no, the interference is constructive. But if a gravitational wave sweeps by, what happens is that space-time is distorted, and like one of the arms stretches a little bit and the other one gets a little bit shorter, and that creates an interference pattern that you can detect. Tiny, but you can detect it. Why do you have 2 of them?
You want to see where the gravitational wave came from.
You can
rise at between different times. And also you can sort out background.
It's the latter. So the former, you get very little information of that. You get the location uncertainty with 2 of them is huge. With the third one that just came out online in Italy called Virgo, it's getting better. Now you can really triangulate. So you're correct, but the really important point is the second one. It's background noise, because the problem you're solving is horrible. You're looking at a problem of 1 in 21 orders of magnitude. To give you an idea, in visual terms, that's roughly looking for an object about the size of a human being, say like about 1 meter in size. in a picture, if this was an imaging problem, you're looking for an object of the size of a person in a photo, not of this room, not of this campus, not of Vancouver, not of planet Earth, but of the entire Milky Way. You're looking for one person in a picture of the galaxy. That's the problem these people were trying to solve. So coincidence is one of the methods that you can use to weed out background noise, because otherwise this would be hopeless. And so in September of 2015, they found a signal that was essentially perfect. This is the signal in Washington. This is the signal in Louisiana overlaid. This is the theoretical model from general relativity numerical simulations for that, and this is the structure of that signal in the frequency, in the time frequency domain. This is a spectrogram of that data. First of all, this is a beautiful example of physics. And second, this is all done. These are Matplotlib figures. This is done. The analysis is done with NumPy. These plots are done with the Viridis color map that was developed for Matplotlib by folks at Berkeley for improved, basically, color perception. Beating the MATLAB one, by the way, beating the Perula one. It has much better color perceptual model than the MATLAB one. And furthermore, they shared all of their work as Jupyter Notebooks. So they did all of their work for us, and by us I mean the entire community who builds these tools, including NumPy, SciPy, etc. This was a huge validating moment, because 15 years ago I was being told, stop doing this, okay? You're throwing away your career, you should stop doing this, get back to serious work, get back to things that matter, like writing papers in applied mathematics and harmonic analysis. Stop doing this nonsense, okay? And for whatever reason, I was stubborn enough not to listen, and I'm very happy to have contributed a tiny little bit to enable this kind of thing. Let's see how much. Unfortunately, we couldn't get the audio to work in full. The background noise is just background noise, but the little whoop, that little blip, that is the sound of two black holes merging 1.3 billion light years away in real time. It's frequency shifted, and obviously they don't make a sound, but it is the exact signal from the vibration, which is it's a strain gauge on the mirrors, is ultimately what you're measuring, converted into audio in the Jupyter Notebooks that these folks shared. And now the LIGO collaboration shares all of their data and all of their analysis, and they make it available both on Microsoft Azure and as binders that contain the code and the data, so that anyone, anywhere in the world, you can click on one of these links and you're running the actual analysis that LIGO uses on the real data from this detection, and they continue to do so. So as new events come out, they continue to release their analysis and their code and their tools as kind of an example of fully reproducible open science. Binder began as a little experiment. We now have funding from the Gordon and Betty Moore Foundation. We have a team of folks in the project working on developing it. It's growing very rapidly. So now we're averaging about 3,000 sessions a week of usage of Binder. It's kind of an experiment. We can't afford to pay for infinite compute for the world, but we want to effectively build a standard for representing computational research that can then be federated to institutions like the kinds of things that are being done here. And finally, very briefly, because I know I'm out of time, I want to talk about how do we deploy these tools in organizations like educational institutions. And we use something called Jupyter Hub, which is part of the project. It's a tool to deploy Jupyter on a larger scale. We're using it. So at Berkeley, a few years ago, a course was started called Data 8, Foundations of Data Science. It's accessible at, this is the textbook for the course, accessible at inferentialthinking.com. And this course tries to basically make ideas about computation and inference available to any citizen. The idea that drove this was kind of a mandate from the university that asked the question, what ought an educated citizen of 2020 know about inference and data? And the idea was, regardless of the major, we're not talking about the computer scientists or the physicists or the statisticians, anyone on campus. And so a course was built to try to make these ideas accessible in a very principled way from an intellectual and statistical perspective, but with minimal barriers to entry. So this textbook was developed. I think the textbook is really a work of art. It's really well done and thoughtfully done. And the deployment is a big Jupyter Hub cloud deployment that has notebooks accessible. As you read the book, you can click on these blue buttons, and every chapter that has a blue button, it will take you to the executable version of that. And actually this morning, testing it here, I discovered that now they've turned it into binder link. So it used to be that if you were in Berkeley, it would take you to the hosted version. If not, it would say, well, you can download it. Now, people at Berkeley get taken to the hosted version, but if you're not at Berkeley, you do get actually access to the live version on binder. This is a picture of the fall edition of that course. This is the largest auditorium at Berkeley. It's called Wheeler Hall. It fits about 700 people. And it was, as you can tell, sitting room only. We have an upper division version of this course, which I'm teaching right now. This was me last week. The upper division one has about 600 students. These are the fastest growing courses in the history of UC Berkeley. We're going to get to the point pretty soon where you will not be able to find a student on campus who's not used to using these tools, who doesn't basically run Python for data analysis as a normal part of their education. We're kind of normalizing these tools at the level of Gmail on campus. The Hub sees a lot of usage, and this graph is a good example of why you want to do these things in things like cloud deployment, so you have a lot of elasticity, because the dynamic range goes from 0 to 500 simultaneous users. And those kinds of variations are kind of hard to absorb if you start putting sort of servers under your desk. And in education, I've been super excited to see that Canada is actually leading the way in the deployment of these tools on a kind of across a really broad spectrum. So folks in this room made a lot of noise in our mailing list recently, noise in a good way, in the sense that you created a lot of excitement with the announcement of these partnerships with Cybera. So I knew of the Compute Canada one, where you folks are partnering with Compute Canada to offer Jupyter-based resources for research and HPC, but now the development of these tools all the way down to K through 12 education is something that is new and very exciting. I've been learning more details about it today, and we need to bring that back to the rest of the community, because when that announcement was made, a lot of people were asking, like, oh my God, who's doing this? What are the details? What's going on? So it's been great. This infrastructure is also used in industry fairly widely. Google, Amazon, Microsoft, IBM, Anaconda. These days, they all have flavors of products that use these tools, which means this is interesting not only because there are kind of industrial services around it, but also because it does provide career paths for a lot of people to work with them and for us to interact as a project with them. So I'm going to wrap up by thanking the people who, in addition to the humans who have done all the work that I mentioned earlier, we're well past the point of sort of nights and weekends open source. This really is a large-scale effort. It could not exist without pretty significant investments from these people. And if any of you wants to learn more or come to, we're now running an annual conference called JupyterCon. It's in New York, August 21 through the 24th of this year. I know there's going to be some people in this room already have homework to do, which is to submit talk proposals to the conference. And I hope to see some of you there. Thank you very much for your time.
So I will let folks go if they want to, but Fernando can take some questions for those of you who can stick around. So, questions?
Yes?
For the Markdown file where you can execute code in it, what is the use case for that as opposed to just using a notebook?
There are people who do write a lot of documents and tutorials in Markdown and who prefer the workflow of writing plain Markdown, and there's nothing wrong with that. And it was, once we had the tools, it was an example of something where if you were to build a Markdown-based editor with the machinery we had before, it would actually be a lot of work. It's not something that we would have built de novo, because it would be a lot of work. With this architecture, it's like, well, we got the text editor, we got the computational processes, we got the console. It's a matter of basically wiring them and doing a little bit of workflow optimization for smart recognition of the block boundaries so that it can do Shift-Enter. And that was it. So it really was one of those things. Once you have the right architecture, certain use cases, you can serve them without too much investment. And there are some people who just prefer to work that way. Why not? Why not give it to them? Yes?
Thanks. So I have two questions actually. The first one is a lot of us are interested in the educational aspect of it, and so I know there are tools out there or services out there that help you to, for example, assign assignments to a student, have them submit, and then even grade them using Jupyter. There is, I think, NB Grader. There is another, the website I recently came by called occupy.org. I just wanted to know if you came by any of these, if you have any recommendation, anything about that. Then my second question is, now I'm not very knowledgeable about this. Somebody was one time explaining to me a downside of working with Jupyter Notebook, and it was about the version control on it. Because like if you open the IPython, the actual file, there's a lot going on in it. Every time you commit it back, it stores a lot of information about the output and things like that. And so if you have anything just talk about that as well.
So first of all, your question is about, the first question, just to repeat it for the recording, the first question was about grading assignments and NB Grader. So NB Grader is a tool that was developed mostly by two folks in the team, Jessica Hamrick, who I already mentioned. So she was a grad student at UC Berkeley. She had to teach a course. She was GSIing for her advisor a course on cognitive, statistical models of cognition, and she wanted to run it instead of MATLAB emailing zip files. She wanted to run it on a hub deployment. So she was actually the first person to build a large-scale Jupyter Hub deployment in the cloud for this, and actually her prototype deployment is what became the foundation of these bigger ones that we're now doing. So this was originally a grad student doing it on her own when Docker Swarm was barely out of alpha. She did so much work on that Docker actually called her to give a talk at Docker, because they're like, we just put this in alpha and you're submitting patches to Docker that show you're doing something pretty advanced with it. Could you come and give a talk at Docker headquarters about what it is that you're doing? And so Jess, as part of that course, she built NB Grader together with Brian Granger at Cal Poly, one of the core leads of all of Jupyter. I'm using it right now. It's not perfect. It has some rough edges. It's definitely not at the point where you can just hand it to someone who has no low-level knowledge, because it's not smooth enough for that. But if you are willing to get your hands a little bit dirty, or you have someone who can do that for you, it works. We're grading the 650-person course. Last weekend I wrote a distributed controller for that, so that we can grade at that scale. Serial grading is not enough because the notebooks that the students submit take some finite amount of time to run, potentially minutes. Minutes times 600 begins to be days. And so now we have, because we run in the cloud, we can repurpose, we can reuse the cluster where they log in. Some of those nodes are available, so we can reuse them to do large-scale parallel grading. And it also supports both automatic grading and human graded input, so that you can both annotate basically the automatic parts, and you can say these things require human grading, and we have graders who then, after the automatic wave passes, then they do basically grading of human annotated input. So it's not perfect, but we are using it pretty much in pretty serious production. Your second question goes to this problem. Your second question is about version control, and it's a very, very valid question. So how do I version control notebooks? If you have a notebook that has changes, and you look at the diff of that notebook, you get this horrible gunk, right? And it's really nasty because the output, things like images are base64 encoded gigantic strings, and you're going to get basically one huge blob of a diff, which is absolutely miserable to read. So NBDime is a tool that was designed for that. NBDime is an open source tool built by folks in the Jupyter project that is designed to basically understand what the semantic structure of a notebook is, what the data structure has on the inside, and to do diffs at the level of the data structure and show you those diffs in a much more civilized and consumable manner. So I would encourage you to look at that. Now, having said that, I'm actually beginning to wonder, I know this is being recorded and maybe I shouldn't say this in public, but I'm beginning to wonder if we shouldn't consider switching to a different format for the storage of the notebooks. Prabhu Ramachandran, who is the original creator of Mayavi, the tool that I was using for my plots in my thesis 18 years ago, he's faculty at IIT Mumbai. He built a little tool called IPyYAML that encodes notebooks as YAML, and is actually capable of separating the output and keeping the input area separate. And YAML is functionally equivalent to JSON. I mean, there's a one-to-one, they're kind of isomorphic, but it's far more readable and far more hand editable. And I'm beginning to kind of toy with the idea that maybe we should switch this, because even with the assistance of additional tooling, the experience is just not great, especially if you're doing a lot of fast collaboration in a team. Right now in this course, we have 2 professors and 4 or 5 GSIs who are all editing and building content quickly the night before all the time. It's miserable. And I admit, it's miserable. So we don't have these are the answers we have, but this story is not over yet. Yes, question, then.
Regarding reproducible research, you seem to be very passionate about it, and this project is definitely geared towards that, right? But I find that I'm not sure if this is, it definitely is the first step towards making reproducible research possible, but I'm not sure if this is actually going to solve the problem in any way, in that it's, the gap is more of how publication is a walled garden as well, combined with the fact that since we want industries to collaborate, they're not always open to sharing this stuff. Do you have any thoughts on how changing that culture might start at universities, because that's where we can make the changes first?
Yeah, so the question is that reproducibility, this is not a complete solution if we consider the issue of publishers participating and incentives. And I certainly don't claim that this is a complete answer. I think it's one small contribution to a very complex puzzle. We are working with publishers, so we actually have right now a partnership with eLife, which is kind of an innovative, forward-looking journal in the life sciences that wanted to try this with us and see if they can effectively include this into the actual workflow of publishing and make it kind of a first-class citizen. And we're hoping to basically get this to the point where it's accepted as a standard and engage first with more scientific societies and publishers that are kind of very open-minded. And if this does become somewhat more adopted, because there is a movement towards improved reproducibility coming from many fronts, this can contribute to lowering the adoption barrier of those tools and kind of changing the culture. But I'm not claiming, I mean, we are doing some of those partnerships, but I'm not claiming that this is going to magically solve the problem. There's issues with data privacy. There's issues with contexts where you simply can't, for legal reasons, share everything. There's issues with the fact that, for example, a very large-scale supercomputing simulation, you can't share the supercomputer, you can't share the entire LHC data set. So I'm not saying that this covers the problem until the end, but it is a partial answer, and partial answers are useful. And they can also provide intermediate steps for solving the bigger problems that they don't solve completely. So I think it's still a worthwhile effort. Yes?
Yeah, so related to kind of the privacy issue is the security issue. So if you have a data set and some data analysis code all in a notebook, and I get that notebook and I can fill in a cell because I want to look at some property of your data. It's got your code and my code, right? So do I want to run this on my machine and trust your code? Will we run it on your machine and trust my code? Or what's the security model?
So the security model of the notebook is that this is weapons-grade radioactive JavaScript. Okay, we have literally built a system designed to do the worst possible thing, which is through web-based JavaScript controls, allow the execution of arbitrary code on the system. Exactly what every security researcher will tell you not to do. That is the whole point of the system. So in a sense, this is a security nightmare. So having acknowledged that, we do have a lot of people looking at it. And because it's useful, right? When people tell us, well, you shouldn't do that, we sort of say, well, that's kind of what we do, right? That's the whole point of the system, is to allow code execution. So we have to allow that, which means what we have to do is we have to build the containment layers around it. And we do have, if anyone is interested here or does security research, I can add you to this. There's a private security mailing list with people, a lot of people in the industry are on that list, and they do security audits. And every now and then we publish CVEs and we have to make fixes, because at least we've tried very, very hard, and folks in industry have looked in a lot of detail at this, at what are the containment and leakage possibilities of the JavaScript security model, so that if, for example, you are running that code on a contained server, what can it do to the rest of your context? I mean, at the low level in the back, at the end of the day, it's whatever the security context of the process, so it's no different than Docker or the VM you're using, whatever. The problem comes with the leakage that the JavaScript layers allow. That is where it gets problematic and complicated. And we do have folks looking at it. We've tried to contain many things. There's actually features that are being slightly removed from the original notebook into Jupyter Lab to increase security and to contain the JavaScript. It's a very delicate problem because a lot of the really nice features of the system come because of the fact that we're allowing so much connection between the front and the back end. So yeah, it's complicated, it's nasty, it's not trivial. It is being used by three-letter agencies. It is being deployed in secure locations. So there are HIPAA-compliant deployments for healthcare data. So it's not the end of the world, but the security, as always with security, it's one of these ongoing things. You have to keep looking because you keep discovering new issues. And if anyone here does security research, get in touch with us. It's potentially a gold mine of really nasty things to discover, which is what security researchers love to find.
Okay, so let's thank Fernando again. If you want to ask any more questions, we'll stay.
Yeah, come on up. Thank you so much for your time.